Here goes. This is a short little instructional video on the EG3000 T series fault locator. This is a locator used on all your low voltage 600 volt insulation or your direct buried jacketed primary. This new design in the ruggedized case, it's got a few changes from the old one, but very similar operation. You can plug the high voltage cord into the side, the output cables, and go ahead and make your connections to your cables that way. You've got now a new battery test up here. We'll give you battery voltage. Same basic functionality, on off. You've got your voltage control, your fault locate, tone trace switch, and then your cable locating functionality over here. On the right side, you can turn the horn on and off. What I've done here is I've connected to a simple little secondary run in a test yard, just to show you kind of what would happen on a good cable. I turn the device on, you see the meter really isn't doing anything. We're not showing that there's a fault, so I'm going to just start throwing some voltage to it. When we get up above 1500 volts, you can see that there's a negative deflection on that meter. That shows me there is no fault. This is a good cable. The pulse is going down the cable, reflecting off the end and coming back in through the positive output wire, making the needle go negative. So that cable is ready to be put back in service. I'm just going to throw the connection over here to another leg, going a different direction down to that end over there. I don't know if you can see the box down there, but 150 feet or so. So throw the instrument back on. 300 volts, we're showing we've got a good fault. And with any fault locating it, before I go out to actually do the pinpoint, I generally just run the voltage all the way up to 3 kV. You're not going to damage your cable at 3 kV. We limit the output current in the device. But the instrument does have the potential to give you a full 3 kV pulse if the conditions at the fault change and it needs to have that extra voltage to keep the fault active. So I'm going to go ahead and set up my detector and get ready to go pinpoint this fault. Another thing I was going to show you before we actually go pinpoint that, this is your charge cable that's physically attached for charging the internal 12 volt gel cell battery. You can leave it plugged in until you're ready to use it, or you can just charge it till it tells you the charge is complete. You're not going to damage the battery by leaving it plugged in long term. It does have a float trickle charger in it built in. There should be a quick reference guide in the locator. This kind of gives you, 9 steps basically to follow when going out there, because we all know nobody reads the instruction manuals. This kind of just gives you the basic things that you need to do on a majority of the faults you'll go on. As it says, the first step in any cable fault, don't forget to do it, is trace the cable. That's why we build in those cable tracing functions into this device. So trace the cable. You will save yourself time in the long run. What I've got here, I've moved down away from my transmitters, clear back over there, and I'm almost near the end of this this cable run. What I've got is my my probes hooked up. These are our new foot probes. We've gone away from the stirrup that you put your foot in to press it in. This is more of just a design where you've got a spike on one end and anybody can put their foot on that and push that in the ground. Longer handles, 2-piece, that come in the new instrument for those people that didn't like the short ones. So this is your typical detector reading when you get near the fault. As I left where my transmitter is hooked up, of course you get real good readings there at your ground rod. That's the collector of all your current flow in the soil. A lot of times, depending on the length of the run, you will lose the signal or get very, very small readings as you proceed down the cable route once you leave the ground rod. When you get near the fault, those readings will start to pick back up because that's where current is entering the soil at the fault. One other thing, just for consistency, once I've marked the cable with my route tracer or cable locator, I proceed down the cable route. As I'm looking down the cable route from my transmitter, I stand on the right side of the cable for consistency with the red probe, like that, in my right hand, because that corresponds to the meter, with red on the right, black on the left. So my black probe's over here. Right now it's telling me this fault is to the right, and so I'm going to pick up and move both probes. I generally keep them, 3 or 4 feet apart. The further apart they are, the greater the reading, because the more difference in potential between those 2 points you actually have. So if you put your probes and run them real close together, you're going to get smaller detector readings just because of that smaller difference in potential. That's why I prefer probes, because I can put them 6-7 feet apart if I need to straddle a sidewalk. An A-frame does the exact same thing. We have those available too. I just prefer probes, but A-frames do work as well. I've placed my black probe where the red one was. Move my red probe out here. I'm getting a little bit stronger reading. I actually turned the sensitivity down a little bit. With our detectors having an analog meter, you only pay attention to the initial deflection. Nothing beyond that, until it comes back to 0, do you want to pay attention to. If a meter moves, an analog meter moves to the right, it's going to move to the left as a bounce back. So just pay attention to the initial deflection, and that only. I've moved my probes one more time. The black probe is now where the red one was. I've moved my red one over here, and I've received, and now I'm getting a reversal. It's telling me the black probe is closer to the fault. So for me, there's probably 100 different ways to do this next procedure, but what I'm going to look for now is a null point. So I'm going to, when I get my first reversal, I'm going to set this down. So I'm going to pick up my black probe, and I'm going to move it back the direction I just came. So I'm going to move it back a couple feet, see what kind of a reading I get. So it's still telling me the black probe's closer, but it's a lot smaller reading. That means I'm getting closer to that null point. So I'm going to move it again another foot or two. Let's see what I get here. That meter's barely moving black on that initial deflection. That's pretty close to a null point. Once you get that null, the real simple thing for me to do is just pick one of the probes. I don't care which one. I'm going to move the red one, and I'm going to split that difference in half. So I've got about 6 feet there, 7 feet. So I'm going to take this red probe, put it at my midpoint between the two, over the top of my cable route. See what I got here now. It's telling me the red probe is closer. Okay. So now I'm going to pull this black probe, bring it into about a foot from the other one, and see if I still get that red deflection. It is proceeding to the red. So now I'm just going to do what we call a 90-degree walk around, and that confirms that I am on the cable route and that I have pinpointed this fault. So I'm going to move this probe over here to the side of the cable route. Still telling me it's red is closer. I'm going to go down the cable route this way. Still telling me red is closer. And then I'm going to confirm on this side of the cable route. And again, it tells me red is closer. So I have essentially pinpointed this fault doing a 90-degree walk around. If that happens and you get 4 points on the 90 that always point to your pivot probe or your center probe, you have successfully pinpointed that fault. You can dig that hole and you'll be money.